So in this video, we're going to look at infinite limits and continuity. Jumping right into infinite limits, if you look at example 1, parts A through H, right? These guys right here, they're all very similar and they're all kind of getting at a certain concept that then we'll kind of generalize in these parts down here. I'd like to start off by looking at these graphically, and then we can go from there and kind of do a numerical approach of sorts, which I'll explain as we get there. So first of all, notice that we have the graphs of f of x equals 1 over x, 1 over x squared, 1 over x cubed, and then to the fourth power, 1 over x to the fourth power, right? So let's start with kind of getting our heads around what they look like. Hopefully we remember this one. If not, add it to your list of graphs that you want to have down. Here, I'm going to do 2 of them right off. So we've got y equals 1 over x, or we'll say f of x equals 1 over x. Looks like this. And then for this guy, we'll call this g of x equals 1 over x squared. And both of them have vertical asymptotes at x equals 0. And they both have horizontal asymptotes at y equals 0. Okay, so just kind of looking at these, just again graphically like we've done before, we want to approach 0 from above. So we're approaching 0 in this direction, and we get these points that are climbing up the curve, and their y values are going to positive infinity. So just off of that, we know that the limit as x approaches 0 from above, from the right, of 1 over x is equal to positive infinity. And then approaching from the other direction, right, this here we're approaching 0 from below. We get all these points here. Their y values are heading towards negative infinity. So that's the first one that they gave us right there, equals negative infinity. Okay, so that's the visual approach for A and B. We're going to come back to that again in a moment and talk about it from a more numerical standpoint. But going to the next one, if we approach from below like this, these points have y values that are approaching positive infinity. And the same thing is happening when we approach in this direction. These points climbing up here are also going to positive infinity. So the first one we approached in orange, we approached 0 from below, so that's this guy. And in green, we approached 0 from above, and that's that guy. And so we can use the graphs of these, which is nice, and it's fine to do it that way. But I think you're going to find, I know you're going to find that as we proceed, you're going to come across functions that are still rational functions like this, but you don't know what their graphs look like necessarily. And so you can't just do this a graphical method. We need to kind of have a sense of what's going on numerically. So if we look at the first one, which is the simplest, if we imagine taking the limit as x approaches 0 from above of 1 over x. Okay, well, let's think about, and I'll do this in green since that's what we have in our picture, but let's think about what the x's are doing. These x's are numbers that are close to 0, but bigger than 0, like this. And I should say approaching 0, right? So here we have these 4 numbers, and they continue on, getting closer and closer to 0, right? Here's a tenth, here's 1 over 100, here's 1 over 1,000, etc., getting closer and closer to 0 from above. Now, when we plug each one of these into the function, we've got 1 over that 1/10. And the next one's going to be 1 over that 1 over 100, and so on and so forth, right? This is putting in the x's as they get closer to 0 from above into our function, which is the reciprocal function, right? 1 over whatever it is we're dealing with. And as we remember from algebra, right? These black fraction bars can be thought of as division. And so we have 1 divided by a tenth, which is the same as multiplying by the reciprocal. Same thing with 1 divided by 1 over 100, that's like multiplying by the reciprocal. And so I'm sure you can quickly see where this is going. We're going to have 10, 100, 1,000, 10,000, etc. So that's what's happening with this. And again, we saw this on the graph, but we want to be able to understand this numerically. The way to think about it is if we have a positive constant over positive close to 0. Okay, any positive constant, 7, let's say, just pulling one out of the hat. And then a positive constant like 2 over this number, right? That's a positive constant, or a positive value close to 0, I should say. That's going to end up being what? Oh my gosh, I don't even know how many zeros I put there. 7 with a whole bunch of zeros. I don't know how many there are there. I'm not going to take time to count. Over 2, which is still going to be 3, 5, 0, 0, 0, 0, 0. It's still huge, right? So this is approaching positive infinity. And so that's the way we can look at a limit like this when we're thinking about it numerically. As we plug in numbers closer and closer to 0 from above, that's going to be a whole bunch of reciprocals, right? And so it's going towards positive infinity, okay? Similarly, if we do the same thing, but we're now approaching, where am I going to put this? Let's move all this down for a moment. If we're approaching now from below of 1 over x, we're going to get the exact same thing that we're seeing here in green, but all of these guys are now negative, making all of these negative, making all of these negative here, right? Making all of these negative, and now we're going towards negative infinity. And so with my little statement here that I did down below, where I had positive constant, right there, positive constant over positive close to 0. Now if we change that to negative close to 0, now we're going to negative infinity. And so there are the first two from a more numerical standpoint. The next one, looking at it numerically, right, the limit as x approaches 0 from the right of 1 over x squared. In this case, you're plugging in numbers close to 0, again, like a tenth, 1 over 100, 1 over 1,000, and they're being squared. So a tenth, when you plug in a tenth down there, it's going to become 1 over 100, which is going to become 100. And if you throw in a 0 here, you're going to get 2 more zeros there, which is going to make it this. And so that's always going to be positive. We're going to positive infinity. Even if all of our x values are negative and close to 0, like this, meaning they're just below 0, when we square those values, they're all going to go positive, so this one's also going to positive infinity. So in this case, or in both of these cases, I should say, we had right there positive close to 0, right? Because we were squaring our negative and positive values, and we got it going towards positive infinity. So there's that. Okay. Next, what happens when we cube numbers? Well, when you cube a number, if it started off positive, it stays positive. And if you cube a number that started off negative, it's going to stay negative, right? So we are plugging in values close to 0, but a little bit less than 0, like negative a tenth, negative 1 over 100, negative 1 over 1,000, etc. That's what we're plugging in for x. But when you cube these, right, when you cube 10, you're going to have 1,000, right? When you cube 100, you're going to have 1 with 6 zeros after it, and so on and so forth. And they'll still be negative. So what we end up with is we end up with a positive constant on top and negative close to 0 on the bottom. So if we come back to this guy, I'm going to keep coming back to this. We've got negative close to 0 with a positive constant on top, which is going to take us to, if it erases, negative infinity. And so here is our negative infinity here. If we approach on the next one, we approach 0 from the positive side, right? That makes all of these guys positive, and we're going to end up with a positive over, right, positive constant over positive close to 0. That's going to go to positive infinity, and I'll show you the graph of that in just a moment. Okay. What do we have going on here with 1 over x to the 4th? Well, no matter what we plug in, positive or negative, when we raise it to the 4th power, it's going to be positive. And so both of these are going to act very similarly to what we had a moment ago here. I keep erasing things back and forth, but we're going to have a positive close to 0 in the denominator, which is going to give us a positive infinity. And so that works for both of these. So we'll go over here and put a positive infinity and a positive infinity. And so just with that much, you might start seeing a pattern. Okay, and it all comes down to whether your exponent on these is even or odd, right? So you'll notice in I, j, k, and l that I'm asking you to evaluate these limits when n is odd or n is even. So if we take a look real quick at Desmos and we type in here f of x equals 1 over x to the n power, and then it wants me to identify what n is going to be, so I'm going to click on that, and I'm going to edit my list. I'm going to have n going from 1 to, I don't know, 20, but I only want positive integers, so I'm going to have it go in a step of 1, and then see what that does for us. Done. And so now here we have 1 over x to the first, right? 1 over x, just like we expected. And if I slide this over and I make it 2, oh wow, there it is, 1 over x squared. And then if I make it 3, it's looking a little bit like 1 over x. You'll notice it's steeper and close to the y-axis and flatter further away. So if we compare that with that, right? Look at x, 1 over x to the first power versus 1 over x to the third power. 1 over x to the fourth is looking a lot like 1 over x squared, but again, steeper, closer to the y-axis and flatter further away. And then x to the fifth, that's looking like 1 over x again, and then x to the sixth looking like 1 over x squared. And so it just keeps going back and forth like this, right? Not super exciting, but the concept is there, because when you have an even exponent in the denominator, no matter what you plug in, positive or negative, you're going to get a positive or non-negative result, right? You're going to get a positive result. And so that's what we have going on here. And so for any time you've got an even exponent on that denominator, you approach from either side, it's always going to positive infinity. Either side of 0 is what I'm talking about. Whereas anytime it's odd, when you approach from the right and the left, it's going to opposite infinities. So that's what it looks like with the picture. Let's go back to what we were doing here. So now, if n is odd, that actually is this situation here and this situation here, right? All of these, okay? And as we saw, depending on whether you're below 0 or above 0, you're approaching negative infinity from below and positive infinity from above. So here, the limit as x approaches 0 from below, 1 over x to the n, when n is odd, that's going to go to negative infinity. And when we take the limit as x approaches 0 from above of 1 over x to the n, when n is odd, that's an n there, we're going to positive infinity. And then when we have an even exponent in the denominator there, x to the second, x to the fourth, x to the sixth, that's these two situations down here, we get positive values in the denominator no matter which direction we're approaching from, because we are squaring or raising to the fourth or the sixth or the eighth. Positive or negative numbers raised to those powers will always be positive. So this is going to positive infinity like this. So there we have that. Now, of course, most of our problems are not just going to be 1 over x to the fourth power or 1 over x to the second or third or whatever. We're going to start seeing things shift around, and we need to work with that. And so we can do this, again, we can do this numerically, or we can just kind of think of the graph. So with part M, what I'm hoping is that we recognize this as still a 1 over x graph, but it's been shifted 5 units to the right. In other words, the graph of this guy is going to look something like 1 over x. So we have a vertical asymptote, right? If we plug in 5 in here, that's what gives us a 0 in the denominator. And we have a horizontal asymptote, and it's looking something like this. If you can visualize that and see, oh, we're approaching from above, right? We're approaching 5 from above like this. That means all these points are climbing up there, and their y values are going to positive infinity. Another way to think about it is if you plug in x's like 5.1, 5.01, 5.001, you're going to subtract the 5, but then you're going to have a positive close to 0 in the denominator, right? Positive close to 0. And of course, you have a positive constant on top. And as we discussed earlier, that is going to take us to positive infinity. Okay? So again, two ways of thinking about that. And as I mentioned earlier, as we progress into these next problems, we're not going to be able to visualize it every time. So being able to kind of see what's going on with this kind of pseudo-numerical approach is going to be the way to go. And we'll get to those in a moment. All right, next one. Well, notice that we have an even exponent right there. So that means that no matter what we're plugging in the denominator, with the exception of 7, where we have a vertical asymptote, we're going to have a positive value, okay? So when you plug numbers in just a tiny bit less than 7, like 6.9999999, in the denominator there, you're going to get 0.00000 whatever 1 to the 6th power, right? Oh, wait, negative, right? Because you plugged in 6.999, however many nines, and you're getting this negative close to 0, but it's being raised to the 6th power, so it's going to become a positive close to 0. So now we've got a negative constant on top, and on the bottom we have positive close to 0. And if you forget what that's going to be, you can just say, okay, well, I've got negative 3 on top, and I've got a positive 1 over however many zeros you feel like writing. When you multiply by the reciprocal, right, this division is multiplying by the reciprocal. Again, I'm not counting my zeros, but that's going to be negative huge, right? Or hugely negative. I don't know, however you want to think about that. But that's going to end up giving us negative infinity. Okay. As far as the graph goes, the multiplying by negative 3 stretches it by a factor of 3, and then you can't tell in the video what I'm doing, but it reflects it over the x-axis. So instead of shooting up like that, it's actually going to shoot downward like this. So hopefully that makes sense. Let's go on. Let's look at a couple others. Going on over here. Okay, so what do we have going on here? Well, if we do direct substitution, which is really what I should have said earlier on, we try that first. I think you'll find that in each case so far it gives you 0 in the denominator, so we have to do something else. But direct substitution here will give me 4 plus 2 minus 6, which will give us 0 in the denominator. So let's see if we can factor that denominator. So we have the limit as x approaches 2 from the left, 1 over, we have an x, another x. Let's see here. I think we can do a 2 and a 3 will multiply to 6. And if I make this positive and that negative, I think that works. And so what you'll notice is plugging into this factor is not a problem. That gives us a 5 in the denominator, right? If you plug the 2 in, you get a 5. But here, this guy is our problem because that's what's giving us the 0. Now, if we think of this, if we break this apart for a moment as the limit as x approaches 2 to the left, or from the left, I should say, and I did something like, here, let's do this in 2 steps. I don't have tons of space here, but I'll do my best. It's the same as this, right? And so we can think of this as just being a constant multiplying. And why am I saying a constant? Because when we plug in 2 here, we're going to be, or close to 2, we're going to be close to a 5th. So the whole thing's being multiplied by a 5th. As a matter of fact, we could even write it this way. And then we could say to ourselves, okay, well, the numerator is basically a positive constant because when we plug in numbers just a little bit less than 2 and you add 3, you're going to be really close to a 5th, right? But in the denominator, when we plug in 1.9, 1.99, we're going to have negative numbers, right? 1.9 minus the 2 gives you a negative 1/10. So we're going to have negative numbers close to 0. Okay, and so we've seen this a bunch of times already, right? I think we had it over here. Positive constant, whoa. So we have positive constant, and then we have negative close to 0. That's going to give us a negative infinity, right? Again, the way you can think of it is if you had that, let's say 1/5-ish on top, and you plugged in 1.99999, however many 9s, subtracting 2, you have a negative 1 over a bunch of these guys, right? And when you multiply by the reciprocal, you're going to have negative some big number divided by 5, which is still a very large negative number. So we are approaching negative infinity in this case. It takes some getting used to, but it's helpful because, again, you may not know what this graph looks like. So that's going to negative infinity. All right, next one. We have a negative constant on top. Direct substitution definitely gives us a 0. So what are we going to do with that? Well, let's see. If we factor the bottom, we have x plus 8 and x minus 8. Okay. Now, plugging in close to 8 here is going to give us 8 plus 8, which is 16. So that's not really the problem. The problem is right there. Okay, so before we look at the problem, this right here is going to be close to negative 1/4. Why am I saying that? Because again, if I plug in something close to 8 here, I'm going to have close to 16. And of course, 4 over 16 reduces down to 1/4. So we have close to negative 1/4. If we're plugging in numbers a little bit less than 8, like 7.99, when we subtract 8, we're going to get a negative 0.01. And so now we have negative constant on top. So over here, now we have a negative constant on top. And then on the bottom, we have negative close to 0. So you can almost think of this as negative 1/4 over negative 1 over, again, do as many zeros as you feel like. When you multiply by the reciprocal, you're going to get something getting positively huge. So it's approaching positive infinity. And so there we have that one. Again, we might not know what this graph looks like, and that's okay for now. We'll talk about methods for graphing something like this a little bit later. Not today. Anyway, moving on. Again, we're going to go ahead and factor, and then we're going to look at our problem factor, and basically the one that's creating the 0 in the denominator. And I think you can see that we have a 0 in the denominator here, but I'm going to keep going here. So we have the limit as x approaches negative 2 from the left. The bottom, x plus 2, x minus 2, like that. On top, we have an x, a 2 and a 4, right? Positive 4 and a negative 2. You can check my work, but I think it works. And of course, we're going to cancel off these 2 here, and this becomes the limit as x approaches negative 2 from the left of x plus 4 over x plus 2. Now, direct substitution is going to give us a positive constant on top, right? That's going to be close to 2, right? Negative 2 plus 4. But on the bottom, when we plug in something just a tiny bit smaller than negative 2, like negative 2.1, and we add 2, this is going to give us negative 1 over 10, or 0.01 is going to give us negative 1 over 100, and so on and so forth. So now we have a positive constant on top, and we have negative close to 0. So do you remember what that's going to give you? A positive constant over negative close to 0, multiplied by the reciprocal, you are approaching negative infinity. So that's what we get for this one. It does come with some practice. At first, the logic is kind of slippery, but you play with it for a little bit and you get there. Look at that. R is the same thing, but now we're approaching from above. So we're approaching negative 2 from above, right? So we're going to have the limit as x approaches negative 2 from above. I'm going to skip down to this step right here because it's going to factor and cancel the same way as the previous one. But now we're plugging in numbers that are a little bit bigger than negative 2. So something like plugging in, for example, I'll do it another color, negative 1.9 is a little bit bigger than 2, or negative 1.99, right? The top part is going to be close to 2. The bottom part is now going to be a positive value, right? Because negative 1.99999 plus 2 is, you're adding something bigger than that negative 1.9999, however many nines, you're going to get a positive close to 0. And so positive constant over positive close to 0, this will take us to positive infinity. All right. A couple more of these and then we'll switch gears. So now we're going to look at some trig functions. Now, it's helpful to know what the graphs of your trig functions are here. Another way to do it, for example, with secant, is to think about cosine. It's reciprocal. So you could choose to do it this way. The limit as x approaches pi over 2 from the right of 1 over cosine x. And then if you think of the graph of cosine, it's doing something like this, right? And right over here, we have pi over 2, okay? And what we're saying is we're approaching pi over 2 from above. So we're approaching like this. And so we have these points getting closer and closer from below. Those y values are getting closer and closer to 0, and they're all negative, right? Right here, right here, right here, right here, right? They're approaching 0 from below. So we have a positive constant on top, but on the bottom, we've got values like negative 1/10, negative 1 over 100, negative 1 over 1,000. So again, positive constant over negative close to 0 is going to go towards negative infinity, okay? Again, another way to do that is to just think about the secant graph. And so you may remember from a trig class, you first graph your cosine like this. We graph our vertical asymptotes like this, and like this. And then our secant graph does something like this. And right here at pi over 2, you can see right in this region, the graph is going to negative infinity. So another way to kind of think about that. Part T, now we're looking at our tangent graph, and you'll notice that if you plug in 2 there, you're going to get pi over 2. And pi over 2, the tangent of pi over 2 is undefined. Okay, so let's go ahead and remember our tan graph real quick. So we have pi over 2 here, and we have negative pi over 2, and the tangent graph does something like this. Okay, now we are plugging in numbers that are a little bit less than 2. Okay, and so that means that when we plug in, for example, 1.9 there, we're dealing with the tangent of a value that's just a little bit less than pi over 2. So we're approaching from here. And each one of those x values has points climbing up here, so this guy's going to positive infinity. And there you have it. One other thing I think I will say about this, you'll notice that these two, the two trig examples here, we're using the graphs to kind of get a sense of what's going on. So it's really helpful to kind of have those at your fingertips. A couple other graphs that are worth having at your fingertips is the graph of an exponential. It goes here at 0, 1. We'll just x, y, we'll just call this one f of x equals e to the x. It could also be 2 to the x, and so on and so forth. And then also knowing the graph of your logarithmic function, which is the inverse. Here it's going through 1, 0. We'll call this g of x equals ln of x. And that one has a vertical asymptote here. This one has a horizontal asymptote here. So these are just 2 more graphs along with your tangent and your secant and your cosine and sine and cosecant and cotangent that will be helpful in doing these. All right, let's go ahead and look a little bit at continuity. So example 2, answer each of the following for the function f of x equals all this craziness, this piecewise defined function. I like to encourage my students to first look here because that tells us where we're going to do different things. You could do this by graphing everything, but we're going to try this without graphing for the time being. Part A, they want us to find f of -2 and f of 3. So you'll notice right here they're telling us what to do when x is -2. Y is 0. That's all. And right here, they're telling us what to do when x is equal to 3 or x is bigger than 3. So we're going to get -3 square root of 3 minus 2 plus 6. That's -3 times the square root of 1 plus 6. I think that's going to be -3 plus 6, which is 3. Okay, so there are those 2 results. All right, now, they want us to find the following limits, and if they don't exist, give a reason why. Now, we're going to first find the limit of the function as x approaches -2. Now, you'll notice here in yellow, if you're approaching a -2 from below, as opposed to here in green, you're going to get 2 different values, or well, let me rephrase that. You're going to approach along 2 different curves, right? If you're in the yellow region, you are approaching along the absolute value function. If you're in the green region, you're approaching along that parabola. So we're going to do 2 limits here. I'll try to stick with colors. Why not? Hopefully you can see the yellow okay. Let's make it a little thicker. So we've got I know that's not really yellow. The limit as x approaches -2 from below of f of x like this. I'm actually going to move that over a little bit. And that's going to give us the limit as x approaches -2 from below of this thing, right? And we can do direct substitution there, and we're going to get a positive 2. Switching over to green, we're taking the limit as x approaches negative 2 from the right of f of x. And again, the reason we're doing this is depending on which side you're approaching on, you have to do different parts of the function, right? The yellow versus the green. So here we're going to have the limit as x approaches negative 2 from the right, but now we're going to use negative 1/3 x squared plus 6, which plugging in a negative 2 there is going to give us negative 1/3. I think squaring negative 2 gives us a 4 plus 6. Hopefully I haven't made any mistakes yet. 4, negative 4. So that's going to be negative 4/3, like that, plus 6, which is 18 over 3, which gives us 14 over 3. And you'll notice that what I'm highlighting in yellow right now and what I'm highlighting in green are not equal to each other. So the left-hand limit and right-hand limit don't equal each other. So we're going to say that this limit does not exist. Okay, and they want me to give a reason why they don't exist. I'm just going to say not equal, right? Right and left-hand limits are not equal. All right, now what? Now we have to find the limit as x approaches 3. So we're going to do the same thing. Let's go ahead and grab all this and move it out of the way. Okay, so now we're going to do the same thing, but we're approaching 3. So let's go ahead and do these two, right? Green when we're approaching 3 from below, blue when we're approaching 3 from above. So we're going to take the limit as x approaches 3 from below of f of x. That's the limit as x approaches 3 from below, and we're going to get negative 1/3 x squared plus 6. Direct substitution, that's going to give us negative 1/3 times 9 plus 6. I think that is what? Negative 3 plus 6, which equals 3. Switching over to blue, we have the limit as x approaches 3 from the right of f of x, which is going to be the limit. Now looking at the light blue region up there, or function, we're going to plug this into negative 3 square root of x minus 2 plus 6. That's going to give us negative 3. When I plug in a 3 here, I think I've got the square root of 1 plus 6, which I think gives us 3. And so because these two are the same, right? Because this guy and that guy are the same, the right-hand limit and left-hand limit, they're approaching the same value, we're going to say this limit is 3. All right, right-hand limits, left-hand limits. So, is f continuous at x equals negative 2? And we also have to check at x equals 3, and crucial, use the definition of continuity. So we've got to make sure we remember the definition of continuity. The definition of continuity says, let's see, let's write f is continuous at x equals a if and only if the value of the function at a, actually I think our book does it in a different order. Let's do it this way. The limit as x approaches a of f of x has to equal the value of the function at a. Now, this is our definition of continuity. This is it. This is what I want you to know. In order for this equation down here, for these guys to be equal, that means that our limit has to exist and our function has to be defined, and the two have to be the same value. Okay? So keeping that in mind, notice what we have at negative 2. So let's just say here at x equals negative 2, f of -2 equals 0 from our work in part A right there, which does not equal the limit as x approaches -2 of f of x, because it's not a number at all, right? So f is not continuous at x equals -2. So there's that one. At x equals 3, f of 3 is equal to 3 from our work up here in part A, which equals the limit as x approaches 3 of f of x, which is from our work in part B. And that's what our definition of continuity says. So f is continuous at x equals 3. And there it is. All right, going on to example 3. Find all x values, if any, at which f is not continuous. Label each discontinuity as removable or non-removable. Okay, so looking at our first function, let's go ahead and factor, because discontinuities are going to happen where the denominator equals 0. So on top we have x, 3, 2, negative, positive, like that. That ought to work. On the bottom we have x, 2, 3. I think they're both negative in this case. And so I'm sure you're noticing that the x minus 3's cancel. And if you remember, that means that we have a hole in our graph. But over here, this is telling us we have a vertical asymptote. Okay, so what we have is x equals 2 is an infinite discontinuity, which is a terminology I actually prefer to what's in the question. The question saying removable or non-removable. This would be non-removable. Removable means that you can reassign a single point or a finite number of points to make your function continuous. So I'm fine with you writing infinite discontinuity here. And then at x equals 3, that is a removable discontinuity. As a matter of fact, I will probably go back to this worksheet and fix it. So changing these instructions, so it's going to say either label each discontinuity as removable, infinite, or jump discontinuity. Jump discontinuity is where the right-hand limit and left-hand limit don't equal each other. All right, next one. We have the top stays x, the bottom factors as a difference of squares, right? Like that. And so we have two vertical asymptotes here. So x equals -5/3 will zero out this factor. And a +5/3 will zero out that factor. So these are both infinite discontinuities. All right, so that takes care of what you have in the rest of this worksheet. So you're going to go ahead and do numbers 1, 2, and 3. Once again, your job is to make a good faith effort on these and follow along with what we did in the previous examples.